Well, welcome to Lecture 8. This is on the structure of primes. So I'm following Jones and Jones elementary number theory, roughly pages 25 to 35 for much of this lecture. So let's start at the beginning. This is a very old result. It's in Euclid's 9th book of Euclid's Elements, and here it is. There are infinitely many primes. So the proof is by contradiction. Let's see how it goes. Suppose that you only have finitely many primes. Let's call them P1 through Pk. Alright, if that's the case, then we can let M be equal to the product of these finite number of primes P1 through Pk plus 1. Alright? You're like, well, why would you do that? Well, I don't know. You'd have to go ask Euclid, right? Now, since M is greater than 1, we can apply the fundamental theorem of arithmetic, right? So that means that there has to exist some prime in the P1 through Pk which divides M, right? But then, what does that mean? That means P divides M, and P divides the product P1 through Pk, right? And since M minus that product is equal to 1, right, that gives us that P divides 1, but you can't have a prime divide 1, so that's absurd, and hence by proof by contradiction we get that infinitely many primes exist. And so it's kind of neat. What is actually kind of more shocking to me is this essentially exact same argument is going to be recycled in this lecture to prove a few other things which look a little bit different, really, but essentially the proof is by contradiction. And it's the other proofs in this lecture are similar in spirit to that. We'll see. I'm not sure that's quite the case for this one, but well, anyway, let's just look at it. Here we go. So the nth prime, P sub n, satisfies P to the n is less than or equal to 2 to the n minus 1 for all n greater than or equal to 1. So the proof is by strong induction. All right. So first of all, it works for n equals to 1 because you get 2 is less than or equal to 2. I think that's true. So suppose it's true for n. Suppose Pn is less than or equal to 2 to the n minus 1 for n equals 1 to k. And now we're going to consider P1 times P2 times Pk plus 1 equal to m. All right. And so, okay, so then there has to exist a prime P which is not in this list, which divides M. All right, because otherwise that would give us that the prime divides 1, which is a problem. So it's a corollary to, I would say this is more of a corollary to the proof of Euclid's theorem than it is to the theorem itself, but anyway. So, okay, so the prime can't be in this list because otherwise we get that the prime divides 1, okay? So since the prime is not in this list, it must be that the prime is greater than the k plus 1th k plus 1th prime, which is not in the list, right? Or it could be equal to it, all right? But the point is that pk plus 1 is less than or equal to p, which is less than or equal to all this. And then we got to do some figuring. So by the definition, by the induction hypothesis, this is less than or equal to 2 to the 2 to the 0, and 2 to the 2 to the 1, and 2 to the what a mouthful, 2 to the k minus 1, which if you simplify, it gives you 2 to the 1 plus 2 plus 4 plus plus 2 to the k minus 1 plus 1. And then we make this step here, which I'll explain down there in a minute, 2 to the k minus 1 plus 1. But so then what we have is p to the k plus 1 is less than or equal to 1/2 of 2 to the k plus 1. That's just literally rewriting this over to here. All right. And, oh no, am I off screen? Please say it isn't so. Yeah, I might be off screen. My bad. Don't worry. If I was, we're not very far past. So we got to here, and rewrite over here p to the k plus 1 is less than or equal to, take that minus 1 power and turn it into a half. So 1/2 2 to the k plus 1 there. And then I take this 1 and I trade it for a 1/2 2 to the k right? Notice that when k equals to 1, that works, and it just gets better when k is larger than 1. So then you get 1/2 plus 1/2, which is otherwise known as 1. And then, of course, that's 2 to the k plus 1 minus 1, which is what we want. We want p to the k plus 1 to be less than or equal to that. So thus the induction hypothesis holds for k plus 1, and we conclude by strong induction that the theorem is true. Now the star step right there is by the little calculation below down here. If we have, let's say s is 1 plus 2 plus da da plus 2 to the k minus 1, then 2s is 2 plus 4 plus da 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 2 to the k. So if I subtract 2s from s, of course I get minus s, but then everything cancels here, chunk, 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 except for the 1 and the 2 to the k. So we get minus s is 1 minus 2 to the k, which gives us that s is equal to 2 to the k minus 1. And that's why it was legitimate to trade this 1 plus 2 plus 4 plus da 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 plus 2 to the k minus 1 simply for 2 to the k minus 1. All right? Yep. So next up here, you're like, what? So this kind of, that's going to be the nature of this lecture. We're going to take some kind of hard turns here as we go on. So next up, the pi of x. So what is this? This is the number of primes that are less than or equal to x, right? Number of primes less than or equal to x. So here's some hard data for you. Number of primes less than or equal to 1, 0. Number of primes less than or equal to 2. Well, there's just 1, it's 2, right? 2.3 is still 1. Number of primes less than or equal to 3. Well, there's 2 and there's 3, so there's 2. Number of primes less than or equal to 24. Well, 1, 2, 3, 4, 5, 6. Wait a minute. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9. What's neat is that there's this, I mean, I'm not sure how neat it is, but here's a prime. Here's a bound for pi of x. It's the floor of the log base 2 of the log base 2 of x plus 1. So remember the floor function, like the floor of 3.2 is 3. All right. And log base 2 is the inverse function of the 2 to the x. So like y equals 2 to the x if and only if x is equal to log base 2 of y. All right, so let's kind of sort through this here right quick. So here's a picture on the number line. Excuse me. Oh, I'm almost out of tea. So, of course, from the corollary to Euclid's theorem, we have that the nth prime is less than or is bounded above by 2 to the n minus 1. So I made this picture to kind of help me think through it. So I got 2, I got 3. P9 is 23. Here's Pn over here somewhere. 2 to the n minus 1 is up here somewhere. All right, and if I think about x being above there, all right, then what I would have is I would have 2 to the n minus 1 less than or equal to x. But the thing is that the log is an increasing function, so it preserves inequalities. So I can take the log base 2 of the inequality, it'd still be true. Properties of log brings out the 2 to the n minus 1. Log base 2 of 2 is 1. So then the next step, I take log base 2 of this, and I get log base 2 of 2 to the n minus 1, because remember again, this is 1. And that's less than or equal to log base 2 of x. But then by properties of logs, this guy just simplifies to n minus 1 times log base 2 of 2, but that is exactly just n minus 1, right? Because log base 2 of 2 is 1. So we get n minus 1 is less than or equal to log base 2 of x, which tells you n is less than or equal to log base 2 of x plus 1, which if you think about it for a second, that means that the number of primes less than or x have to be greater than or equal to the floor of that function plus 1. You can just keep the 1 outside the floor if you want, whatever. Because you know, the number of primes up to x is what? It's these guys, right? So there's at most n of them. Anyway, there's that one. So that's kind of a neat estimate, although it's actually, as pointed out in Jones and Jones, pretty useless. So like, just to give you a sense on how weak that bound is, here's some numerics on the problem. Log base 2 of 10 to the 9th by the change of base formula. Log base 10 of 10 to the 9th divided by log base 10 of 2. And that's 9 over log base 10 of 2, which is about 29.9. And if you take log base 2 of that, you get log base 10 of 29.9 over log base 10 of 2, which gives you 4.9. And then if you add 1 to that, and oh look, now I'm taking the floor of the whole thing. It doesn't really matter if you add 1 in before or after the floor, it does the same. But of course the floor of 5.9 is 5, so this the weak bound gives you 5 primes. There's at least 5 primes less than a billion. Yeah, so if you look at it, and I haven't done this personally, so I'm trusting other people because I have other things to do with my life than count all the primes up to a billion. But if you look at it, maybe if you had a summer, I don't know, you can figure out that there are 50 million primes, about 50 million primes below a billion. So while it is true that 5 times 10 to the 7th is greater than or equal to 5, I don't think 5 is really a very good bound on that, is it? Now there are so many results that are known about the structure of primes that I'm not going to cover in this lecture. I'll just say there's a lot more known. There's people who make a living studying this kind of thing. And here's really one of the first results in the direction that those kind of folks are interested in. And so this is, I would call it's an asymptotic result, all right? So like, here's the result. Pi of x is approximately the integral from 2 to x of dt over log t. So this was conjectured by Gauss in 1793 and then proved by Hadamard and Poussin, I don't know, 1896. Another way to look at this is that pi of x divided by x log x goes to 1 as x goes to infinity. Another way to say this is that pi of x is approximately equal to x over log x for large x. All right, and here's a little calculation to kind of confirm that. This is not a proof of the prime number theorem, mind you. This is just a proof that this formula for pi of x and the formula x over log x for pi of x, that they're asymptotically equivalent. All right. And I think I have seen the distinction between this formula and that formula made explicit by people who know more. There's more to say here, all right, but this is kind of like the 0th order discussion of this topic, so I'm just going to stick with it. Anyway, so to show that this formula and that formula are essentially the same for large x, if we could show the limit of this goes to 1, it would say that basically it would say that this and that are growing at the same rate, so they're asymptotically equivalent. Anyway, so first of all, if you want to compare things, it's good to have them either 0 over 0 or infinity over infinity, so you can apply L'Hopital's rule. So my first move was to move the log x upstairs rather than downstairs. Once I did that, then I've got something that is going to infinity over something else that's going to infinity. So I can apply L'Hopital's rule. And when I differentiate it, I got product rule, right? Because it's a product of functions of x. And the derivative of x, well, that's easier, it's 1. So the fundamental theorem of calculus part 1 says the derivative of the integral with a variable bound is just the integrand evaluated at x, which in this case gave me 1 over log x. So that log x over log x gave me that 1. And the other one left me with an integral dt over log t over x, which then, upon my second application of L'Hopital's rule for this indeterminate form, end up with 1 over log x over 1, which then goes to 0, and I'm just left with 1. So I think this is a homework problem in Jones and Jones. Maybe I'll still assign it, just to be friendly. So, here's some data supporting, just to try to bring to life the idea here. If you look at the number of primes in 1 to 1,000, there are 168 of them, as it turns out. If you look at 1 over the log of 1,000, here, what's 1 over 1 divided by the natural log of 1,000? What do you got? 0.145, right? So what's 160? You compare that to 168. 168 divided by 1,000 is 0.168, right? So I get that, and I'll divide by the 0.168 because I remember it. What does that give me? So, it's about 14%. It's about 13% off, relatively speaking. And anyway, if you calculate these, they're about 10 to 20%. Probably less. Probably like less than 15% off. If you compare 1 over log x versus pi x, which is, you can figure out from here, right? Like, what's pi of 2,000? Well, pi of 2,000 would be 168 plus 135, and 168 plus 135, that would be the number of primes less than, 2,000, 303 apparently. So if I take the natural log of that, if I take the, divide by 2,000, right? So I get 0.515, that's pi of x over x, all right? Compare that to 1 divided by the natural log of 2,000. What do I get? 0.13. So I forget what I had. 1.5 was it? So I'm about 12% off. I don't know. So they're close, but they're not quite matching. And so I went ahead and I consulted Wolfram Alpha just for kicks. There are 78,498 primes less than 1,000,000. And if you calculate 1 over the natural log of 1,000,000, you get about 0.0724. And if you calculate 78,498 divided by 1,000,000, you get 0.0785. So it seems like there's a discrepancy between pi x over x and 1 over log x, which continues even for pretty large numbers. Well, large in my view. Perhaps not large in the viewpoint of. So anyway, just to give you kind of a sketch of where this goes. I used to work with a fellow who did this kind of thing for a living, and he'd be looking for like patterns in the primes, and there's some sort of like probabilistic sense in which they behave, and so you can kind of look at them and study their distributions and so forth like a probability theorist, and you can say a lot of things. So these that's the I would say that what's known as analytic number theory is that kind of thing. But anyway. So here's another proof which is shockingly like the proof of Euclid's theorem, and yet is saying something quite different. It's saying something similar in the sense that it's also saying something about there being infinitely many primes, but now of this form, of the form 4q plus 3, meaning that the prime is equal to 4 times some number plus 3, all right? And so this is one of many results on various forms of primes. So I'm just going to show you this one and talk a little bit about generalizations of this one, actually. But here's the proof by contradiction. Suppose there exist finitely many primes, p1 through pk, of the form 4q plus 3. Construct m equal to 4. Now, like, why construct m like this? No one ever explains why. But anyway, using the process of mathematical tradition. This has been handed down by our mathematical forefathers, so we do it. For P1, PK, I'm sure there's a subclass of mathematicians who can explain this, but I'm not in that select guild, sadly. For P1 through PK minus 1, And if you tilt your head and squint, you can rewrite this m as 4 times p1 through pk. That's just where I have here, minus 1. So if I subtract 1 here, that's like subtracting 4 overall. So if I had minus 1 to start with and I subtracted 4, I have to add 3 to get back where I started. So this is just an identity. This is equal to that. But this being equal to that shows that m is of the form 4q plus 3. All right, where q is that? Now, what else can we say? Well, m is odd, right, because it's of the form 4q plus 3. And that means each prime that divides m must either have the form 4q plus 1 or 4q plus 3, because odd numbers are either of this form or that form. Think about it. So all of the m's factors are either of the form 4q plus 1 or 4q plus 3. If they're all of the form 4q plus 1, notice that 4q plus 1 things times 4q plus 1 things, for example, 4s plus 1 times 4t plus 1, it works out to 4 times some number plus 1 again. So it's still of the same form. So it cannot be the case that all of the factors in my m have the form 4q plus 1, because otherwise if I multiply them all together, I would get another number of the form 4q plus 1. And as we just explained, m is of the form 4q plus 3. And these are distinct categories. These are partitions. The odd numbers can be partitioned into these two disjoint classes. All right. Anyway, so it must be the case then that there's at least one factor of the form 4q plus 3. All right, scooched up here a bit. So there's at least one factor of the form 4q plus 3. And so we've got p divides m, and we're going to call that one factor p. All right, so we've got p divides m, and p divides all of these guys, right? Because, why is that? Oh, because we're assuming there's finitely many primes of the form 4q plus 3, right? So it has to be in our list, right? Which means p is one of these guys. But you also have that 1 is equal to all of that. So you've got p divides this and p divides that, which means p divides 1. Oh man, the prime divides 1 again, so a contradiction. So there must be infinitely many primes of the form 4q plus 3, because assuming there's finitely many leads us to a contradiction. Now, there are also, it turns out, infinitely many primes of the form 4q plus 1. We'll talk about this much later in the course when we use something called Gaussian integers. It turns out a rather different way of thinking is needed to properly digest this problem. Otherwise, you have to work really hard on it at the moment, I believe. And the place that the current proof breaks down for the 4q plus 1 kind of things is that if you look at the 4q plus 3 kind of things, when they multiply together, you end up with something of the form 4n plus 1. So you notice that there was this sort of divide and conquer strategy used in the proof, and it made us look at 4q plus 1 times 4q plus 1. So if you flip the problem over and you had 4q plus 1 playing the role of 4q plus 3, you'd end up looking at like 4q plus 3 times 4q plus 3. And when you did that, you wouldn't be able to rely on this theorem that 4q plus 1 times 4q plus 1 is 4q plus 1, because it's not the case when you multiply 4q plus 3 type things. You get a 4q plus 1 type thing. So, oh well. So something else is needed for that problem. And the secret sauce, whatever it was that it took to solve that something else, was learned by Dirichlet. In 1837, he proved a sort of grandiose mega version of this theorem, which is that if you have the GCD, if you have coprime integers a and b, then there exist infinitely many primes of the form aq plus b. So this is his big theorem on arithmetic progressions. This is above our pay grade. But Jones and Jones mentions that it's proved in Apostles' number theory book, which is formidable. I think Apostle is a very good author. Previous generations of math students learned calculus from his calculus book. Some of them anyway. So let me just talk a little bit about some famous conjectures about primes. There's the twin prime conjecture. There exist infinitely many twin primes. So like 3 and 5, 11 and 13, 29 and 31. So people tend to believe that this is true. I mean, we've found tons and tons of these things, but no one can quite prove this yet. So it's interesting though, right? Because like the things we were just talking about basically say that the primes are spreading out. They're getting thinner, and yet even though they're getting thinner, they're still coming in pairs. So it's kind of, there's a tension here logically between the twin prime conjecture, right, and the density results we were just talking about. There's also Goldbach's conjecture that every even integer larger than 2 is the sum of two primes, like 4 is 2 plus 2, 6 is 3 plus 3, 8 is 3 plus 5. Again, a lot of people have tried to prove this. No one's been able to prove it yet. And I think both the twin prime and the Goldbach conjecture have been like verified for very large numbers on the computer, but again, that's not a proof. Now here's a conjecture that didn't turn out well. Okay, or maybe it did. I don't know. Kind of depends on why you want to look at it. His conjecture, I guess, it at a minimum, it spurred further activity in the field, and it made other people think about it. So it was useful, even though it was wrong. And Fermat's conjecture was that numbers of the form 2 to the n plus 1 are prime. And that's true for the 0, the 1th, the 2nd, the 3rd, the 4th, F4, right? 3, 5, 17, you might recognize as primes. 257, I don't recognize it as a prime, but I'll take its word for it. 65,537, also prime. Again, okay. But Euler in 1732 showed that F5, which is 2 to the 5th power, that's a 5 there. My green marker is kind of devolving. Plus 1 is this number, which happens to be 641 times 6,700,417, which in 1732, without a calculator, he figured out. And the way he figured that out, I will kind of walk you guys through, and there's a homework problem for that one. So you can kind of appreciate how Euler saw it, because he did not have a calculator, obviously. Anyway, point of order here. Numbers of the form 2 to the n plus 1. These are called Fermat numbers. Primes, which are also Fermat numbers, are called Fermat primes. All right. They're interesting because, among other things, Gauss showed in 1801 that a regular k-gon, regular k-sided polygon, was constructible via compass straight-edge methods if and only if k was equal to 2 to some power times the product of distinct Fermat primes. So it's like, okay. Yeah, that's one of the things, like, Gauss solved a problem of Euclidean geometry that had just been sitting there unsolved for 2,000 years. That's the kind of, statistically unusual intelligence that Gauss had. And yet many people still have, dim opinions of him today because of the way he treated his peers. I think there's a lesson to learn there. He should be nice. It's better to be nice. But anyway, if you read some quotes of things Gauss said about teaching, it's really like, I would not have agreed with him, I don't think. He was kind of mean, but maybe I should be meaner. I don't know. Anyway, distinct Fermat numbers are mutually coprime. It's kind of neat. So even though they're not necessarily prime, if you look at them pairwise, they don't have any common prime factors. So if D is the GCD of two distinct Fermat primes, say Fn and Fn plus k, then you can look at x to the 2 to the k that has root x equal minus 1. And so you can factor out x plus 1 times g of x for some polynomial g of x, right? And if you plug in x 2 to the n, you get 2 to the n to the 2 to the k minus 1, which by algebra is 2 to the n plus k. And then I add 1 and subtract 2 to get back to the minus 1, just to see that this is f to the n plus kth Fermat number minus 2. It's equal to the nth Fermat number times some other number, which shows you that this guy, well, it shows you that 2 is a common divisor of both the nth and the n plus kth common n plus kth words, Fermat numbers. But if 2 is a common divisor, that means that if 2 is the GCD, then that means that the if D divides, if the common words, if the GCD divides 2, that means that the GCD is either 1 or 2, and it has to be 1 because the Fermat numbers are odd. So, yep. Oh, incidentally, that gives you another kind of sneaky proof that there are infinitely many primes, because if there are infinitely many Fermat numbers which are mutually coprime, it must be that there are infinitely many primes that form those coprime factors. Anyway, here's another theorem which I think has been left as a homework exercise I may or may not assign. If m is greater than 1 and a to the m minus 1 is prime, then a equals 2 and m is prime. Gay. Anyway, integers of the form 2 to the p minus 1, where p is prime, are called Mercene numbers. A prime which is also a Mercene number is called a Mercene prime. Here's some numerical examples of these, like 3, 7, 31, 127, 20. These are all primes. And then this one, not so much. See, 2047, which is the M11, is 23 times 89. So I guess as of 20 years ago, when Jones and Jones was written, there were something like 35 Mercene primes known. In the last two, when the text was first edited, were these two. By the time footnotes were added, there's another 2 that are listed in the book. I haven't had a chance to look up how many are actually known, but I would guess a few more have been found if I had to guess. You know, it's been 20 years and we got a lot better computers, so you want to say there might be some more found, but I don't know. I haven't looked it up. So, next up, primality tests. So we started the previous lecture with the proof of this one. An integer n is composite if and only if it's divisible by some prime p, which is less than or equal to n. All right, technically I only prove one direction of the if and only if, but you can prove the other. And here's a more interesting example of that, 97. So 97 square root's 9.85. So we should check, what, 2, 3, 5, and 7. So here's 2, then 3, then 5, then 7. As you can see, there's a remainder in each case, which means it's not divisible by any of those, and therefore 97 is prime. So, pretty cool. Now, there are other tests based on digits in decimal expansion, like the rule of 9s for checking divisibility by 9, and we're going to talk more about those in a future lecture, so I'm going to omit them for now. I think this is a worthwhile comment to make right here, right now. That if you look at it seems like this is a useful test, right? But if you start thinking about big numbers, it's actually pretty bad. Because the number of primes being less than square root of n, that's approximately, so like pi of square root of n is roughly square root of n over log n, which is something like, 2 root n over log n. And if you look at n equal to 10 to the 100, which would be something like a 100-digit number, then you can calculate that 2 to the root n over log n is about 8 times 10 to the 47. Now I tried to just plug that into the calculator and it didn't like it. You have to kind of like work your way around. Like the calculator does not behave well. Here, see what happens when you try to do square root of 10 to the 100? What do you think is going to happen? Yeah, math error. See, it's not happy about that. So you have to kind of work your way around the square root with algebra and that kind of big number calculation, just something to be aware of if you're trying to crunch numbers. Sometimes you have to work your way around what the calculator's limitations are. Or, of course, you could go to Wolfram Alpha and it could probably just do it. But Anyway, the point of this is that that is a lot of tests, and with standard computers, the amount of time it would take to do that is something like the billions of years. I mean, life of the universe, if you believe in that sort of thing. And anyway, so that means checking if a really large number, like a number with 100 digits, is a prime, is computationally intense. It's pretty much just too much to do with this naive method. So you need other methods to factor, or to test the primality of very large numbers. And so ultimately this is what encryption rests on. Something called RSA encryption is basically based on this difficulty, that it's very, very difficult to factor large numbers into their prime factorizations. So anyway, we'll talk more about that in a future lecture. It's called RSA encryption. That's basically how your email is safe. I think it's, by the way, a little bit shocking that that's an application of number theory, but it is. So finally, we have reached the end. This is the final primality test I'll talk about in this lecture. It's the sieve of sieve of that guy. So the way this works, so this is one of those things, if I was smarter, I would just write the odd numbers, because we already kind of know what happens with even numbers, right? And that could like cut the work down a lot, So that's the first thing. But I didn't do that because, well, I don't know why, I just didn't do it. So let me just work through it here. So what we'll do is we underline the first prime, which will be 2. All right, and then underline the primes, cross out multiples. So what are multiples of 2? 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 42, 24. So a smarter thing to do if you're really going to be using this method and not just trying to illustrate it like I am at the moment would be to just write the odd numbers down to start with, because you already know that you're going to cross these all out in the first step, so it's kind of stupid. All right, so next up, 3. I'll do it in a different color. We underline the next prime. All right, so what we're trying to do is figure out primes up to 60 for my example, all right? So you write down all the numbers from 1 to 60. You don't really need the 1, right? Write the numbers up to 60, and then you start underlining primes, and then getting rid of all the other multiples, all right? So like 3, 6 is already gone, 9, 15, 21, 27 is a multiple of 3, 30 is already gone, 33. 39, 3 times 13, right? 45 is gone. Multiples of 3, 57 is a multiple of 3, isn't it? Yeah. All right, so we got rid of those. What's up next? So the rule is the next number that you come to has to be a prime after you've crossed out all the multiples of the primes which come before it. All right? So I'm going to run out of colors here pretty soon, but 5 is the next one, right? So I cross out multiples of 5, but I think I already have. So 10, 15, 20. Oh, I didn't get 25 yet. No, it's gone. 30, 35, oh, gone. 40, 45, already got that one with the 3s. 50, 55, oh, they're gone. All right. So we got rid of all the multiples of 5. All right, what's up next? Let me see, I need another. Here, I'll use gray this time. All right, here we go. Here we go. Exciting. 7. Multiples of 7 that we haven't already got. 14, it's gone. 21, dead to us. 28's already gone. What's that? 5 times 35 is already gone. Multiples of 7. 42 is already gone. Oh, 49. That's 7 times 7. Now it's gone. Ha ha ha. I think that's it. So again, the rule is the next number we come to that hasn't already been crossed out must be a prime, as it is. Ooh, hey, I do have this pink marker I never use over here, don't I? So that's prime. And then any multiple of 11 we have to cross out if it's not already been crossed out. 22 already gone, 33 is already gone, 44 is already gone, 55 is already gone. All right, so at this point we can actually stop, because I think everything's left has to be a prime. Why? Because we're looking for, like, square root of 60 is what? Square root of 60 is, what, 8? Less than 8. So actually by the time you get to 7, you should be done, because there can't be, how to explain this, but we're done. And if you look, 13, 17, 19, 23, 29, 31, twin primes, woohoo, 37, 41, 43, another pair of twin primes, what do you know, 47, 51, 53, primes. So anyway, that's it. So thanks, guys.